prefer to sit here. It's easier.
How will you flip the slides?
But
How will you change the slides if you sit there?
yeah. so
No, but if you sit there, it's it's easier for us to see you. It's better that way.
Switch on. Locked in. You don't have to keep this one.
what?
Copy it on the desktop.
Yes.
Take this. Start. So green was blue after her.
Yes.
Then
Green.
let's start.
I'm Leila Chubin and I'm going to talk about control of deposition rate by locally charging the vapor in order to create high aspect ratio features in this presentation. At this time, there are some methods to do deposition and make high aspect ratio features. We need to make high aspect ratio features because we need them for some applications, such as in filters, sensors, and other applications in research or in the industry. Some existence method that now people use in industry or in research. Also, we use that in our clean room. One of them is lift-off metallization. As you can see in this figure, this is very, very easy method and very common. A lot of people use that, and also I am working with this method at this time. At first, we have a layer of photoresist and expose that. We have the pattern. After that, we deposit metal on the photoresist layer, and by cleaning, after finishing deposition and cleaning, we have the pattern in this way, in this shape. This is very good and very common method, but it's not possible to use this method when we need high aspect ratio, because having a very thick layer of photoresist is not possible. It's hard to manage the deposition and also cleaning at the end. Another method is LIGO. This method is combination of lithography, electroplating, and molding. As you can see in this figure, at first we have a mask, X-ray mask, and we expose that by X-ray. Then we use etching, and after that grow high aspect ratio feature by electroplating, and at the end we have the features as mold. Because we use X-ray and also X-ray mask in this method, both of them are very expensive, and that leads to we have an expensive method. This is very good when we need high aspect ratio feature, but that's very expensive, and it's not possible for us to use this method for all of the applications that we need. Another method that some people use for the research but not widely used is localized electrochemical deposition. It's very easy. As you can see in this figure, we have a current monitor, we have a microelectrode, a positioner, our substrate, metal substrate, and a probe. We could change the position of the probe, and also we charge the probe and the substrate, metal substrate. The sign of the charge are opposite. We have a chemical here, That chemical contains some charged metal atoms that by changing the charge of the probe, by changing the amount of the charge of the probe and also the location of the probe, we could control the deposition rate and also the height of the deposition, the amount of the deposition. This is another method that we propose here, and very, very analogous to the LED, is localized electrostatic charge for physical vapor deposition. We need, in this method, we need only to control the particles by electrostatic charge, and we do not need to have any chemical reaction or any chemical. We only work with probe and our wafer or our substrate. There are two ways to do this method. One of them is charge probe in proximity of the position area. Another one is charge probe applied to the opposite side of the wafer. If we want to have deposition on one side, we use the probe on the opposite side of the wafer, not on that side. As you can see in this figure, this is our wafer. We charge that, and also this is our probe. We could change the position of the probe in X, Y, and Z direction. We charge the probe negatively. Maybe we have not only one probe, we could have two or twice. That depends on our application. And also wafer charge to increase the particle adhesion. Both the probe and wafer are charged. The probe attracts particle to the location of the deposition, and the charge on the wafer helps the particle to help its particle adhesion, and also prevent the particle from being deposited on the probe. Another way to do this method is using probe in the opposite side of the wafer. We want to have deposition in this area, but our probe is behind the wafer. By changing the location of this probe and also changing the amount of charge on that, we could control the deposition rate and also the position of the deposition. This method is better than previous one because we are not worried about the deposition of metal on our probe, and disadvantage of this is that maybe wafer spread out the charge and cause deposition to be less localized. Advantages of our idea is that we could control the probe position in X, Y, and Z direction, and by controlling the probe position, we could creating arbitrary shapes, not only a rectangle, not only a cube, or a very thin layer. We could control the shape. We could make whatever we like by controlling the position of the probe. And this method is cheaper than the previous one, such as LIGA, because we do not use any X-ray or any chemical. This is very easy. We only use current and charge the metal and the wafer. This method can be used with any type of physical vapor deposition and not restricted to metal. We could use that with a lot of range of material, not only metals. And in this method, we do not need any chemical and any chemical reaction. There are some challenges with using this method. One of them is that we may need to charge the material positively or negatively, and keeping the probe free of deposition is very hard. Maybe we need to coat our probe with some special material to prevent the deposition of metal on our probe. And throughout issues is very important. Maybe we couldn't make a lot of features by this method. We could use multiple probes to speed up our process. Future works in this area is simulation to assess feasibility, creation of prototype, extension of concept on this method to an inkjet-based pattern control prototype, because a very similar method to this used in inkjet-based pattern control prototype. In summary, we proposed a method of creation of high aspect ratio feature by localized electrostatic charge in physical vapor deposition. It may be possible to create previously unachievable structure with this method, and also it may be possible to control the deposition pattern. Questions? Yes.
Why are you worried about deposition on the probe? It's under the wafer, right?
We talk about two ways of doing this method. One of them is we use probe behind the wafer. Another one we use probe on top. I could show you.
Yeah, right. But your method is for using.
This is one method, right, and another one is this. In this method, we are worried about the deposition of metal on our probe.
Okay.
and that one, this one, we are not worried about this.
Okay. And I have another question. If you apply charge to the wafer, aren't you worried about localized heating taking place on that wafer?
Localized?
Heating, like, oh, that area of the wafer can get heated up if...
Heated?
Yeah.
You mean the current makes some heat?
Yes. Is
But
it
I
possible
think-
for that? Is it possible for heat pockets to develop if you use this method on the wafer? Like you are applying charge on that area, right?
Yeah.
Is it possible that that much part of the wafer can get heated?
So there's no problem. Maybe I think the amount of heat is not a lot in this
Okay.
because we do not use a lot of current,
Okay.
and our wafer is big. If you have a probe, maybe that makes some heat. I didn't think about that. Maybe we need to use some cooling, and that, or think about that. But I think the amount of heat is not a lot to be worried about.
Okay.
Okay, another question? No question?
When you say localized deposition is easy process, what metrics to use? Why do you call it easy?
I told localized deposition is easy.
So the other
I told lift off process that we are using in nanofab at this time. It's not hard. It's easy. Lift off metallization.
So why do you want to do this then?
Because by lift off deposition, lift off metallization, we couldn't have high aspect ratio features. The amount of deposition is limited. By this, we could have high aspect ratio.
So you mean we cannot deposit thick metal and do lift off?
The thickness is limited, and also the pattern. You know, when we want to have something like that, the pattern, something like that, I think this method maybe work. But when we use lift off and we use a layer of photoresist and then deposition, the thickness is the same in everywhere.
Where we might need some structure like this?
Why?
Where would we need structure like this?
Maybe we need.
Okay.
And another thing, I think.
Pardon? Can you go back a few slides?
Okay.
Another-
Which one? This one?
This was what there was localized.
Localized electrochemical deposition.
So can't we get the same thing from this?
The same as this.
Yeah.
I think we could have something like this from this method, but we need to use chemical and the controlling of this, because we have the charged metal atoms in chemical. It's that method I think is easier than this, because that's physically, not chemically. And also, when we have here copper, copper, there are also oxygen and something else, and that maybe makes some contamination, and we couldn't have a very good deposition layer. But with that layer, with our method, we use physical vapor deposition. We do not have anything else. We only have metal atoms, not anything else. And the controlling of the process and also the cleanness, there is no contamination, that's easier. And when we want to have a lot of substrate, not only one wafer, by using this method, you should repeat the process, and maybe you should have a lot of this but by our method you only need to have some probes to do that.
Right. Let's thank Leila.
Good morning, all of you. I'm Manisha Mohan, and my topic is fabrication of thick silicon dioxide layer. The focus of my paper was on two processes that can be used for fabricating thick silicon dioxide layer by deep reactive ion etching process and photoelectrochemical trenching. The properties of thick silicon dioxide layer is that it has a thickness of 10 to 100 micrometers, and it provides very good insulation like electrical, thermal and mechanical insulation, and they find the application in high temperature sensors and RF inductors where insulation is very important. So why do we use silicon dioxide layer for insulation? The reasons are they are easily grown, they have very good quality, the thickness can be precisely controlled, and they are very compatible with standard semiconductor technology of fabricating. We know some oxidation techniques that can be used to form silicon dioxide layer, but these techniques cannot be used to form thick silicon dioxide layer because in the first method, which is thermal oxidation, we get a good quality of silicon dioxide layer, but it's a time-consuming process. To form a thickness of 30 micrometers, it takes hundreds of hours to form such thickness. And the second method, which is chemical vapor deposition, is a faster process, but it yields poor quality of oxide. And the third one is the anodization process, which is again a fast process, but the oxide which is formed is porous, and they don't have good insulating properties, so we cannot use this process also. And that's why we use deep reactive ion etched based oxidation, which is basically a lateral oxidizing process instead of the usual ones where the oxidation happens vertically. So here in the first step we form silicon pillars, that is high aspect ratio silicon pillars with a ratio of 0.8, and this ratio is the ratio of silicon pillar width to the trench width. So if we have a ratio of 0.8, then we can have good oxidation. This process is followed by wet oxidation at 1100 degrees Celsius, and this process is not the vertical oxidation, but then only the silicon pillars are oxidized horizontally. And then it is followed by trench refill, which is done by LPCVD technique, and this is mainly done in order to avoid voids, because in the wet oxidation process there are voids formed, and so LPCVD technique removes it. So this is how the process looks. Here in this process, the silicon pillar depth determines the oxide thickness. So if we want a 30 micrometer thick silicon dioxide layer, we have to etch the pillars for a depth of 30 micrometers, and the oxidation time depends only on the lateral width of the silicon walls. So if we want 100 micrometers, it takes the same time as it takes for a 30 micrometers, and the only factor that affects oxidation time is the width of the silicon pillars. So the problems that were faced in this method was the formation of voids. This was due to the non-ideal sidewall profile. Though we use deep reactive ion etching, there are possibility that the walls are not perfectly straight, so that can cause deformation, and the pillars are not properly oxidized. So this can be overcome by filling the oxidized wafer with LPCVD for further closure of the voids, or we can also change the sidewall profile like this so that we have pointed trenches at the bottom and wide trenches at the top, so that the bottom trenches are easily oxidized and the top portion can be oxidized by LPCVD, so even this can be used. And there were tests and observations based on this silicon dioxide layer, why it is used. So when we checked the test, when we did the test and observation, we found that the thermal conductivity of silicon dioxide layer was 1.1 watts per meter Kelvin, and we can see that it in this process, this is the silicon dioxide. This is silicon dioxide ring, and inside it there is a heater. The dark portion shows a lower temperature and the white portion shows a higher temperature. So we can see that this silicon dioxide layer prevents the dissipation of heat to the outer surface. So this is a good insulation material. And it can sustain extrinsic shear stress up to 3 to 5 megapascals. And it breaks only at 22 to 32 psi. So this is a good insulating material. And the next method that can be used to form the thick silicon dioxide layer is the photoelectrochemical etch, in which the first process we form V grooves by using KOH etch because they're selective in this direction. And this is mainly done to initiate the etching of HF electrolytes. And this is followed by steam oxidation, which forms completely thick silicon dioxide layer. And the experimental setup consists of anode as a silicon wafer and platinum electrode as cathode, and the electrolyte was 1:2:17 of HF, ethanol and water. Here the illumination was provided by 300 watts halogen lamp, and it was a backside illumination. We can see it here. So when the halogen lamp was switched on, there was photonic absorption here, and there was generation of holes which reacted at the V grooves, and that's why we had the V grooves etched previously. So the trenches were formed by dissolution of silicon, and this is how it looked after the formation of silicon pillars, and this is how it looks after oxidation process. Here we can observe some uneven surfaces which can be overcome or smoothened by metal polishing. So the advantage of photoelectrochemical etch was that it's a low-cost alternative. It's less complicated when compared to the first method, and there were no voids formed because of the type of etching that we used. But the disadvantage is that it forms a permeable oxide layer, which cannot withstand high pressure or shear stress when compared to the previous method. So we saw about two methods of lateral oxidizing process that can replace long thermal oxidation and deposition techniques to form thick oxide layer. So there are research going on to reduce the number of voids formed in the process, and also to form large areas of oxide layers. And even this method is extended to titanium and other materials to form thick oxide layer for insulation. Thank you.
Questions?
So I'm confused about one thing. This is I'm not very familiar with this area, but I realize the difficulty of growing the thick oxide. Which part is the proposed? Which part is already done? Which parts are you proposing to do with the
Actually, I haven't proposed anything. I have just addressed a problem that is faced in forming of thick oxide layer, and these are the methods that can be used to address the problem.
Okay, so these are methods that we can do right now.
Yeah, the deep reactive ion etching and the photo.
Could you talk a little bit more about that membrane forming one? Come up a little bit.
For this one? Oh, actually, what we can do is we can isolate the insulating material. So this is just to show we can isolate the material by back etching of the silicon. So here we had the silicon wafer, and it was back etched to form a suspended thick oxide.
Oh, I see. So basically you etch not the oxide but the silicon, and then you oxidize the membrane. Is that right?
No, we don't oxidize the membrane. This membrane is the oxidized portion of this.
I see.
So the dark portion shows the oxidized part, and this gray portion shows the wafer, the silicon wafer, which we can etch to to isolate it. It's like a pattern, like we can form. For example,
so you form the pattern, you oxidize. Do you etch away what was that pattern, or what that pattern becomes the oxide?
So here we use a silicon ring, which means we want only the silicon ring, like only this portion.
I see.
So in order to get that, we can etch away this portion, and we can form a silicon ring.
Now. Thank you. Nice.
How does that perforated part become all black?
This part?
Yeah, the left one is, you see, this is silicon.
Yes. The dark portion shows the oxidized part
How does that become all black?
because this is the silicon wafer. And this is the process of this. Now this is kept in the furnace and we are oxidizing this wafer. So what happens is that these portions, they all get oxidized. And they're completely oxidized into silicon dioxide. So there are no traces of the silicon vapors. So there is oxidization in this way.
So then the oxide which is growing from both sides, you think it's going to merge into each other?
Oh yes, they'll merge into each other. But since both are of the same material, there won't be any other interactions between them.
But they will be just in physical contact, they'll be not making a continuous sort of a film, isn't it?
Yes, they'll be forming a continuous sort of film, and that's what we want. We don't want any non-complete oxidized wafers, so that's actually acceptable.
Interesting. What's the reference of this? Do you have reference of this one?
I have it in my paper.
Oh.
Yeah.
Can you go to the next slide? So here they're not doing the oxidation, here they're doing LPCVD.
Yes, it is only not completely LPCVD, but for example here, it's an ideal process, it's an ideal way. But this is not how the wafer will look after oxidization. And there will be some parts that are voids. So in order to fill up the voids, we do finally LPCVD method too.
So even after this, there will be voids.
Yes.
That's what I was saying, that they will
Okay.
come together from both sides, but there will still be parts where they may not be in contact with each other.
Yes.
But
So
those
that's
are filled by LPCVD.
LPCVD. Yes.
So we can, so instead of now we are doing two processes. We have to first etch this guy, then do oxidation,
Yes.
then do LPCVD or PCVD.
Only when we have voids. If there are no voids, we don't have to do LPCVD.
Then versus just put the wafer inside a furnace and leave it for 20 hours.
Yes, and we'll get a thicker oxide.
So which one is better then?
Because if we don't etch them and if we place the wafer inside the furnace without etching them, we will get an oxide layer, but then we'll not get a thicker oxide layer because of diffusion rate constraints.
So when you say thick, how thick would we need it?
Or we can have from 10 to 100 micrometers
You
thickness.
can't have more than that in oxidation furnace?
We can have, but then the time consumption is very high. It takes hundreds of hours to form 30 micrometer thickness of oxide layer. Only by keep placing them in the furnace.
But on the other side, we have to do this processing on this guy.
I don't understand.
Because we have to do first etch silicon. like
Yes.
this. Then we have to do oxidation. Then we have to LPCVD
Yes.
to fill up any void.
Yeah, it's not a time consuming process. So this is basically done to reduce the time taken by the thermal oxidation process.
You said something of aspect ratio 0.8, right?
Yeah.
This specifically has to be 0.8?
We're talking about
Yeah.
0.8.
Yeah. the aspect ratio.
Approximately 0.8, so that we get a completely oxidized layer.
Why is it has to be just 0.8? Why can't we make the pillars thicker or?
Yeah, we can have like 1.5, 0.8, around 0.8 we can have, but I don't know why they've chosen 0.8, but it was stated that 0.8 is a perfect ratio for having a good oxidized layer. So for example, here, if we have the silicon wafer thickness, the pillar thickness to be 2, in this process the pillar thickness was 2 micrometers and trench thickness was 1.5 micrometers.
Why I'm asking because as we know that when we do oxidation on silicon,
Yeah.
44% of the silicon gets consumed in the silicon dioxide
Yeah.
forming, right?
That's right.
So that's why maybe it has something to do with that ratio. or
Yeah, it
percentage.
should be.
If it's less than 0.8, then the silicon dioxide won't
Yeah,
be
that's why I'm
there,
asking
right?
why it has to be 0.8.
So it's a thermal oxidation?
What?
Thermal oxidation.
Yeah, it's a combination of DRI and thermal oxidation instead of having just thermal oxidation alone, which is a time-consuming process. And And silicon dioxide, thick silicon dioxide layers are having their applications in many sensors where insulation is important, so it's becoming popular.
Any other questions? Right. Thank you.
Okay, hello everyone. I'm MD Shajib Raihan. So I'm going to present my topic that entitles a new lithography technique over EUV lithography and its prospects and challenges. So this is my agenda for today's presentation. Abstract introduction. Then I will go through some basic concepts of EUV. That means extreme ultraviolet lithography. Then I will discuss some benefits of EUVL. Then the challenges we face in EUVL. Then I will going to present my proposed lithography technique. Then the future recommendation. So this is my abstract. So I'm going to summarize that EUV lithography is nowadays is a very promising technique. So why it's promising? Because it uses exposure wavelength at 13.5 nanometer. So, but the thing is that due to extremely short wavelength and reflective nature of EUV, it makes the system vulnerable to flare and shadowing effect. So, what is flare? Flare is a surface roughness. So, due to flare, it is very hard to correct for in EUV lithography. So my proposed technique will be able to overcome this problem, and I named it feedback lithography. And the thing is that it will be with this technique, it will be able to have exposure wavelength below 13.5 nanometer. So this is just if we just overview that from the past, several expertise groups determined that which technique will be viable in future, as you know the technology has been scaled down so far. So we can see that in 2001 NGA workshop survey, from the figure 1 we can see that the prospect of EUV is much higher than comparison to other techniques, and you can see from figure 2 that 2006 Sematech lithoforum also surveyed, and it's very obvious that EUV lithography was popular. So and the popularity has risen. Okay, if I discuss some basic about EUV lithography, it is basically called soft X-ray lithography, and the exposure wavelength used, as I told, that is the 13.5 nanometer, which is 1/10 of the previous technology, previous lithography technique. Like before using EUV, it was like 193 nanometer as for exposure wavelength. So there are some problems here, like we cannot use conventional lenses in extreme ultraviolet lithography technique. instead we can use multiple reflective systems as mirrors. So some guys showed that molybdenum and silicon composition exhibits high reflectivity at 13.5 nanometer wavelength. So low reflective material can be made also, but we need 13 mirrors here. So one is one can be used as a mask surface, and other 6 mirrors can be used as illumination optics, and other 6 can be used as position optics. And of course, the accuracy of projection pattern is very high in UV lithography. So this is the actually basically exposure system, but I will not go into details. This is just how it looks like. The thing is that UV also deals with Rayleigh's equation, and we know the minimum feature which is provided by Lord Rayleigh, and the equation is R equals to K1 lambda by Na. We define K1 as a process constant and lambda as a exposure wavelength, and Na as a numerical aperture. And if we compare with EUV with 193 nanometer lithography technique, so what do we find? So from the at the bottom you can see there is a there is a ratio between EUV minimum feature over 193 nanometer minimum feature. So you can see that from the relationship here, this mark here. So, and for numerical aperture that is used for EUV is basically 0.45 to 0.5, and for 193 it's 1.35 is chosen. So from the equation, if we compare the ratio, you can see that in case of EUV, this is 5 times better than 193 nanometer case. So of course it's better, but there are few obvious challenges in EUV lithography. So what are the challenges? My desired surface roughness could be less than 0.1 nanometer, but the thing is that due to it needs extremely sophisticated technique for polishing the surface, but it's very hard if we go below the 13.5 nanometer wavelength. And of course, if you use multi-layer mask, then it would be another challenge to produce a defect-free mask. And other point is that like very slight thickness variation and very small numbers of particles can produce the layer rough, and so if we use several masks, then on top of the layer, on top of the bottom layer, it will be like it will be really rough, and our process might be damaged. So there are also some challenges, like UV requires more mirrors. As I said, that one expertise showed that 13 mirrors is required for UV technique. So of course it's a challenge, and since no mirror is a perfect reflector, so and due to radiation exposure is lost by reflecting. So, and UV is not good option when we look forward to below 13.9 nanometer as my exposure wavelength. So what can be the possible solution? What I propose, actually one guy proposed that they used optical proximity correction and phase shift mask technology, but the thing is that I use different criteria. Like I will call my technique as feedback technology. They use different algorithm, I use different. So obviously optical proximity correction and phase shift mask can be used also my proposed technique, but I will put it for future work. but I will show you what is the basic mechanism for my technique. So I call it as a feedback lithography, and the thing is that due to feedback lithography, we will be able to achieve exposure wavelength below 13.5 nanometer, which is used for EUV. So before then that, we have to make sure that there are some criteria like photoresist, SS diffusion, then flare, then shadowing effect, pattern loading. So all the things must be overcome with this technique. So the thing is that this technique will it be able to overcome these can I say challenges? That is the question. So the proposed model functions similarly as feedback system. That's why I named this as feedback system. Like you can see that in control system there is some open loop system and closed loop system. So closed loop system as a feedback system. So that's why I used this term as a feedback lithography for my case. So what can be done more in feedback lithography? OPC, that is optical proximity correction. I said it before. This method modify mask amplitude, and what is the purpose for phase shift mask? That actually produce favorable constructive and destructive interference to remove my shadowing effect, or I can say that it can increase my intensity of exposure light. So this is actually this is not my technique. This is actually the optical proximity correction that can be incorporated in my technique as well. That's why I put this picture here. So this is the typical scheme of optical proximity correction, and this is the phase shift mask, and also this is the typical case which has been used by other guys. And if we incorporate both OPC and PSM in a technique, then we can get better resolution, either using only one, either OPC or PSM. And here comes the main point. What I actually used as a what mechanism I used for my case. I used like different. I used two methods. That is, one is inverse method, inverse feedback method. Another one is forward method. So I'll show you the figure later on. And okay, what does inverse method do? Inverse method, for inverse method case, we have to first take the optimized pattern or the desired pattern of mask. Then we later on we from the figure we can see. Is it visible? Like at first we take desired mask, then then I compare with my uncorrected or input mask with my desired mask. And you can say that uncorrected mask as input mask. So when I get the error, like where I can correct this, and I can make such an imaging model so that I can correct or I can improve my error. So this is the actual iterative system. So this is how I'm actually using here inverse method. Why it is inverse? Because I'm actually going from the output. I'm actually taking the output as my first step. Then I'm comparing with my uncorrected one. So that is how through this feedback model I can improve on my uncorrected mask. And for the forward feedback model, I take uncorrected mask as input, and here is the block transfer function. I didn't generate any equation for that, but it can be said that if we generate a function so that it can be modified later on, and we can use the modified mask for imaging model. That is also should be an ideal model, and there should be an correction checker where my mask is getting wrong, where there is error on mask. So it's also an iterative method, but it's forward. It's not as inverse feedback model. So how I can do this iteration? I can use like MATLAB for simulation and check in every step either I'm getting the improvement or not. So that's how I can use the MATLAB 2D model, 2D diagram, not 2D, it's 3D. Like in x-axis I can take OPC, and y-axis I can take PSM, and z-axis I can see that where my optimized point. So that's how I can get my optimization. Okay. So and the thing is that for imaging model, all possible parameters must be taken into account to have the minimum error. Okay. So what I recommend for future works, like current model can be developed so that the concept is, I can say that my concept is viable, but we have to choose such a method so that my concept can be implemented further. And for OPC optimization, for this feedback lithography should also be developed, and also in case of PSM, that should be also developed. And if we incorporate both OPC and PSM together in the feedback lithography, then I can get my desired mask. Okay. So this is my references. So thank you. That's all. Is there any question?
How can you change the mask?
As I said, that mask like when I decreased my exposure wavelength, like from 13.5 to then when I actually want my desired mask will be printed on my surface, like, but due to shorter wavelength, it's not actually possible. So I actually will modify it on. I will first test it that which mask can be used so that I can get my desired layer on top of the surface.
Right, but your feedback model or feed-forward model, either case, both say modified mask. How are you going to change a printed mask?
Okay, modified mask. No, so that I can I have to generate such an algorithm so that I can modify it. I said that I can use MATLAB or other software for simulation purposes.
I'm having the same trouble understanding. Is your mask in software at this point? Like, are you basically simulating a mask and modifying it until you get it right, and then printing the final result?
No, I'm taking the pattern. And
so you take the mask, you transfer the pattern on a wafer or something.
Yeah, right.
Exactly. Take the image and then compare that output with.
I take the dimension. Then actually with such an algorithm I can
it's kind of try and error method.
It's like an iterative method. It's like an iterative method that I will compare with the desired mask pattern to the input mask.
Then you have to design a new mask
right.
Each time you modify it.
Exactly.
Yeah,
Exactly.
So how long can that go on?
How many
masks? Because mask generation is a very expensive thing, right?
Yeah, it's just a concept. So I can say that if we could do that, we can go beyond, below 13.5 nanometer, and we can scale down our devices further.
Look at the number of masks you are wasting.
How do you say we can go below 13.5 nanometer?
Oh, as I said that.
The mask design allows you to use.
No, as I said that for UV lithography, 13.5 nanometer is used, but when I go beyond that we cannot get the exact pattern as mask on my wafer. So due to surface roughness, and I also said that shadowing effect and as well as flare. So due to some criteria, we cannot.
But that is not the exact reason why we can use the wavelength below 13.5 nanometer. There is pitch limitation and critical.
Yeah, exactly. So I also said that there are two things, that OPC, like optical proximity correction and PSM like phase shift mask. So OPC is used to adjust the amplitude of my lens, or you can say mask.
But using OPC will minimize your critical dimension also, because
Yeah.
when you do optical proximity correction, your minimum feature size decreases, right?
Yeah.
Because of the small HSL patterns that you do to get a perfect shape, perfect corners.
Right. So what is it?
My question was, how does it modifying a mask allows you to use shorter wavelength shorter than 38.5?
No. A shorter wavelength, I can use like shorter wavelength, but it can destroy my pattern, mask pattern on the wafer. But if we take a iterative step so that I can choose my desired pattern at first, desired pattern, that this should be my desired pattern on the wafer. But since it's not happening, so I will just iterate due to with the either inverse method or forward method, and I will check what's the error, and I will take different pattern of mask. Like it can be first initially rectangular, so I will make it circular, then see what can be the shape on the wafer.
Yeah, but what has that got to do with the wavelength of the system? I mean, you're changing the masks, not the wavelength.
No, I will, of course, I will change the wavelength. I mean, you know the Rayleigh criteria. So there is a. So here is the Rayleigh equation. So if we just for EUV case, if we reduce this one, I said that we will have several problems like surface roughness, and we cannot actually use lens as for EUV because we use mirror. So we'll check, we'll reduce the wavelength, and we'll see that for which wavelength I get the exact pattern of mask on my wafer, which I have which I can get from the feedback lithography method.
So you won't change your mask then?
I am changing mask to get the desired wavelength.
If we use this iterative method, this modification in the mask, that will allows you to transfer the
Pattern
perfectly in a wafer even for shorter wavelengths.
Yes, that's what
So
I'm saying.
wavelength remains constant. I mean, you can't change more.
So he's basically,
dimension will be less.
Dimension will be less. Afterwards, dimension will be less. My
Yeah, but
total
your
dimension
source
will be less.
will be like.
So there, it's like costly. Initially, it will be costly to get the idea that which wavelength we can use ultimately for.
Okay. Go back to your feed forward.
Which one?
Any your that feedback and feed forward block diagram, the last slide I guess. Yeah. That error detector, or what is that signal? Is it the image of the final pattern, or is it the light that is reflected?
No, not light. It's the pattern of mask and the pattern on the wafer. Like if I put a rectangular mask and if I get like zigzag pattern on my wafer, so there is error. So where the error is being happening, so I will check with my error detector. So, but this is just the concept. This is a mechanism. This is not the implemented thing. So, that's why I put some future work here that we can do it later.
So you're looking at the pattern of on the wafer, right?
Yeah.
And then accordingly you will you will modify your mask to suit the pattern.
Right.
So you're
So same
modifying.
wavelength.
So the wavelength.
For the same wavelength.
Yeah. But the wavelength will have to be the same, right? If you're
You can change one parameter at a time.
Yeah.
You have two variables. That's going to be.
Right. There are three variables actually. Like we can increase numerical aperture. Either we can decrease my wavelength, and as well as this is actually constant factor. So yeah, two parameters. But for optimization case, I guess it might be possible to decrease K1 as well.
But practically, it's not possible. You see. You have to start with one technology and optimize it for that technology. Technology means a specific wavelength you're using.
Yeah.
Yeah, I guess you are changing your mask every time, so you have to keep every other thing constant.
so right. So
What I
you're
got that
changing K1.
using
right?
this method
Right.
will
You're changing
definitely
one
increase the efficiency of the photolithography, but maybe it will not allow me to use shorter wavelengths.
Right.
That's, it will,
For one
it will improve
specific
the efficiency of the photolithography process.
Right,
How
for
quickly I
that
can transfer the
technology,
picture.
for one specific technology.
Yes.
Yeah. So I'm not implementing. That's why I said that I can
But
simulate.
it's useless if it's not implemented.
No. I can simulate.
Building castles. So stop saying that I'm not implementing that. If it's not feasible, then it's the whole idea shouldn't be discussed.
No, it might be feasible if we just simulate and check. I mean, different algorithm can be made to check either it is okay or not.
Sajid, one question. How is this different than regular optical proximity correction and phase shift mask methods?
Sorry? How?
The current state of the art in OPC and PSM is something like this, right? You take something and you shift the mask until you get the pattern you want. How is this different?
The difference is,
than what's currently
like
done?
you see that from here that I use like rectangular mask and I got here this shape, and if this is my corrected mask, that's what I'm saying, that I will change my mask and we'll see that first of all let me clarify this. I use this mask but for below 13.5 nanometer. Okay, I use a particular wavelength for below 13.5 wavelength. Then I got undesired pattern, so I changed my mask such a way so that I can get the desired.
I understand, but how is this? What do they do currently? I mean, isn't this how optical proximity correction is done right now?
Yes, that's true.
So what is the difference? Or like what are you proposing in addition?
I'm actually proposing that it's an iterative method and it's feedback method.
I see. So
you see,
so
that
that
I'm
only
taking the feedback.
What you're suggesting is
just changing
keep iterating on it until
until
perfect.
we get the perfect pattern on the web.
Okay, sorry, I was unclear on that.
So how the stimulation is accurate?
Sorry?
How do you guess your feedback stimulation will be accurate? How do you agree? Because the stimulation is based on some theory, right?
Yeah, based on
that
theory.
It will be like some.
You know that in control system you just compare with your desired output. I like reference output with the input, and you check what is the error. Then after that you use a different model. That's what I am saying. That here is the imaging model. So I can build an imaging model such a way so that I can get my desired model, or no. If not, I can get as close possible to that pattern. So it's like a concept
What is the
here.
advantage of this technique comparing the traditional technique?
Original technique.
Yeah. So why is this advantage?
It's like actually what I'm proposing, that it's like a iterative system so that I can get the.
You mean reduce cost or better performance or what?
Initially the cost will be high, but when I get the exact mask, then I can use a wavelength that is below 13.5 nanometer, and at that time I can get scaled, what can I say, reduced size of my device.
But how can
The main purpose is to reduce my device.
But how can you do that? You found your perfect mask for one particular wavelength, and then you will reduce the wavelength. So then again everything will change.
So
right?
that's why actually I initially I said that I cannot go below 13.5 nanometer, but my purpose is to go below 13.5 nanometer wavelength to have the reduced dimension of my device.
Let's wrap it up. Can go on and on. Let's wrap it up. Yeah, I know that's thanks, G. But the point is that yes, this is something that has instigated discussion, and that's leave it on. In some places we haven't had any discussion at all, so it speaks for itself. Want to delete it?
No, I rename.
Doesn't matter, it's gonna get deleted when we log out from the computer.
Okay.
Because when you dump it here, I don't get it from this computer. You know how to get PowerPoint to me. We discussed it yesterday.
Yes, yesterday we discussed.
how to do. All right, so that's good. So how it works, we probably haven't gone too deep into OPC, but once we have a technology, we saw the image at least that we have this design, but this is what we get, which falls short at corners and edges. So from that, a mathematical translation is defined, and a matrix is defined, which basically tells us what is the function of translation. Where at different points, it will be different translation. Right? We know matrices. We apply transfer functions with matrices. Right? This mathematical multiplication where one point multiplies the other, plus second and row multiplies with second and column. Right? So, and we get a resultant matrix. If I get back, we can get back to the original matrix. But now we know the transfer function, and we can change that transfer function to change the output. So your input stays the same, but your output will change because now you are applying those transfer function to the mask design. But you can't iterate the wavelength at the end, as of now. Maybe that is what is your idea that's hard for us to understand. That maybe we can not only change the transfer function, we can go back and change the wavelength as well and define a new transfer function. But now we are dealing with two variables. But how many knowns we have? So we can have two variables, and we need to have two equations to figure out. But if there is one equation, so that's probably more deep analysis if you want to do. If you want to look at this, that you don't want to change wavelength, then we have to see how many variables that we have, how many equations we can get. But OPC, the very fundamental concept is it's a mathematical transfer function that we change, that we apply to get a result, which translates into making some parts smaller, some parts bigger. Right? So that's the change which you get. So we are halfway done. Probably we have seen by now the good, and I don't want to say the rest. So we have seen some good talks, some not so good, but that's part of the game. Probably that's why submitting it early was advantageous to some, because now you're going last, so you know what not to do. So this is what we have done last week. This again, upload it here and upload on the. We have looked at oxidation, right? So this is just an example that if you want to have silicon dioxide, but we cannot use silicon. In one case we saw, Manisha was talking where we can oxidize and then we do CVD. So CVD is what we do if we don't have too much silicon to spare. And quite often this is the case for SOI wafers, where we have silicon on an insulator and we don't have too much silicon on the top above that valid oxide. So if I use this up, I will not be left behind to make my devices. So what I want to do is I would instead deposit silicon dioxide. So when we do this deposition, essentially what we are doing is we are not reacting the material at the top, we are depositing. So for oxidation, if you see the word growth, that will mean thermal oxidation where you are consuming silicon. But if you talk about oxide deposition, we'll be talking about one of this methods, CVD or PVD. Right. What is PVD? Physical vapor deposition. And what is CVD? Chemical. So both differ in nature. In one case, there's a chemical reaction that results into the resultant species to get deposited. In another case, it's just that we have this solid material, we heat it up, we make vapors out of it, and we deposit those vapors. We heat it up maybe by just applying heat or by using E-beam to melt it. In any case, this is the basic idea of deposition, that you want to deposit material from outside. There is a long list of materials that can be deposited. And what defines the deposition is some materials stick well on others, some don't. So we may want to use sticky layers on that. So that's a material that will bind, will stick, adhere to both of those materials who don't bind to each other. Very common example is, if you don't know yet, I've started lecture already. So the common example is titanium and gold, titanium or chrome. They stick well to silicon dioxide, but gold doesn't stick directly to silicon dioxide or silicon. Right? So we use a thin layer of titanium or chrome.
As adhesion layer?
Adhesive layer, sticky layer, right, to put our gold on top of that. So they are also.
How thin does a layer need to be after the top?
Monolayer. All you need is a monolayer.
So maybe several
monolayer for different materials is different thickness. Generally, it's about 10 nanometers. So if you want to put a monolayer, means if you want to cover everything, it has to have at least 100 nanometers. But it depends on different materials.
So we can't just deposit gold and expect it to stick.
Yes. Yeah, it will come out very easily next cleaning process. So that was just one example. So there are many different combinations of what we used to do our deposition to make sure that it sticks. So that's PVD, right? So CVD is a simple growth model. We flow in things in there and we let them react. We get the material deposited and then we get our film. So in this case, it depends on either it's a temperature-driven reaction or it is an energy-driven reaction. Both cases, in one case we are using heat to provide energy for reaction. In another case, we would do plasma at lower temperature to provide energy for the reaction. So, but in case of temperature, it would be called LPCVD. In case of chemical, it's called, in case of direct electrical energy, it's called PECVD, plasma enhanced CVD. So they both have their own pluses and minuses. So we put polyfill, we put silicon dioxide, nitride, tungsten. So the recipes also define what kind of polycrystallinity you get. So these are amorphous or polycrystalline material when we deposit. So we can change their property by changing the recipes. What would go into a recipe? What would be all the parameters that go into a recipe of a CVD process?
Well, there's the source and energy.
Source means, so it's not only the gases, their proportion. How much of neutral or noble gases we pump in to dilute their reaction, right? And energy, how much heat, what temperature, or what power we have to apply, right? So temperature in case of LPCVD, power in case of PCVD. And for how long, right? So that would define your recipe, which would result into what? A film. And what would be the desired properties in a film? What would be the properties that you want to change in a film? Thickness, growth rate, right? So how quickly you want to get to your thickness. And roughness and density, right? Yeah, density of the film, because that would result into different etch rate, different defects in it, right? You may have many more pinholes with one recipe and not with the other. Density and tensile strength. That stems from the polycrystallinity, right? So what kind of polycrystalline material do you want? You want networks to be long or small, so they're all is dictated, because that results into this tension, the what you call the mismatch between those polycrystalline surface and the crystalline silicon below. That will result into certain tensile, what you call tension in the film. If you ultimately make a membrane, then it will matter that do you want it to be under strain or not.
So is CVD always, does CVD always result in polycrystalline material?
No, it depends on your recipe. Depends on your recipe. Right? So that would result into larger regions of crystalline formation or smaller of those. Of course, when you put tungsten with its metal, there's no crystallinity to that. So it depends on your recipe. So what do we want to get out of it? We want to get good thickness uniformity, which means that it's the same thickness everywhere. So if you have a full wafer, it should not have variation, or variation should be within tolerance. Yes. Yeah, so tolerance, we can't have it perfect always. What we can live with is, it should be within tolerance. Maybe 5%, 10% depends on our process. And purity, high purity, not just in the material, but the byproduct shouldn't get incorporated itself. Right? So we want to have a recipe that gives us pure surface. And many times you want it to be highly dense, right? Maybe it's not the case, because sometimes we just need to put a sacrificial layer which we will have to etch later on, so we don't care if it's highly dense or not. All we need is to cover it completely. Composition doesn't change across the wafer. We know stoichiometry, what is the number of molecules, atoms that come together to form something, some network. Perfection, structural perfection, good electrical properties. Maybe we want it to be insulated, maybe we want it to be electrically highly conductive, which is the case in polycrystalline, polysilicon, right? Heavily doped polysilicon. Now, there's another factor from the outcomes that you want. We may not want it to be doped. So our outcome may be heavily doped polysilicon, because it's going to act as a metal, and it's going to act as a gate. Or we may not want it to be doped. So we can do what is called in situ doping. From our recipe, we can get heavily doped polysilicon. Or we can do doping by conventional way. How do we do doping? Diffusion, right? Or impartation. But we can do it in situ as well while we are doing that. So it may be whatever electrical property, conductive, insulator, whatever you want. Good adhesion, good step coverage. It should cover everything and shouldn't have too much defects in that. So how do we achieve those? So this CVD advantage over others, it gives you highly pure outcome, because the product that you get is result of a reaction, so you are making those reactants to come to the surface of your wafer. So what you get is very pure right there. It gets made up right there and gets attached on the surface. Unlike PVD, where your source is away from the wafer, and you melt it and you let the vapors travel to the substrate, right? So we'll see at PVD